Okay, so in this problem, we want to do quite a few things. We're going to kind of move in from approximating the area underneath the curve with a fixed number of rectangles, and then after that, we're going to go from that into the infinite sum. And the definition of the integral to calculate the area under the curve, the exact area under the curve. And then at the end, we're going to use the fundamental theorem of calculus to find the area underneath the curve. So that we have a way to compare all three methods. So the first one is we're going to approximate the area underneath the curve from 0 to 4 using 4 rectangles. Okay, now this isn't necessary, but I'm going to draw the picture. I'm going to draw this graph right here so that we get a visual of what's going on. So this is my axis, and then y equals x squared is a parabola. And what I'm looking for is the area underneath the curve from 0 to 4. So let's say 4 is right here. And so what we're looking for is the area from 0 to 4. Okay, so the first thing we're going to do, let me put little tiki marks here, 1, 2, 3. Okay, so let's say we're going to do all three. We're going to do a left approximation using the left endpoints. We're going to use the middle endpoints, and we're going to use the right endpoints. Okay, so let's find some important information. We know that delta x is equal to b minus a over n. And, well, remember that a and b are just your, represent the endpoints of your integral. So a here is going to be 0, b is going to equal 4, and we already know n is equal to 4. So that means delta x is equal to 4 minus 0 over 4, which is 1. Okay, and then delta x, remember, tells me the width of my rectangle. So, for example, here for the left-hand approximation, I'm going to start off at 0. Remember, we said that's going to be our first point. And the next one is going to be a distance 1 away. So I would use 0, 1, 2, and 3. And then for the right endpoint, remember, you start not with the first one but with the second one, so you would use 1, 2, 3, and 4. And then for the middle, what you do remember is that you grab the point in the middle. So in this case, it would be right in between 0 and 1, which would be 1 half, and then 3 halves, 5 halves, and then 7 halves. Okay, so let's why don't we draw this picture? Since we're going to do the left one first, let's draw the picture of what the left-hand approximation looks like. So here, my first value is 0, so I go up to 0. Well, the function at 0 is equal to 0, so I have no rectangle there. But then at 1, I go up to the graph and then across, and I'm going to find the area of that rectangle. Then my next value is going to be 2. I'm going to go find the value of the function there. and that's going to give me the area of the next rectangle. And then I'm going to go up at 3, and that's going to give me the area of my very last rectangle. So let's add these up. So here, so the, let me separate this, make sure we don't go across. Okay, so using a left-hand approximation, the integral between 0 and 4 of x squared, oh sorry, I forgot the differential here, dx, whoopsie. This is equal to, the first rectangle has a height of 0, so this is going to be 0 times the base of the rectangle, which is 1, plus the height of the rectangle when x is equal to 1, well, this is equal to 1 squared, right, times the width, which is 1, plus the height of the rectangle at 2, well, that's going to be, well, at 2, my parabola is 4, so this is going to be, so let me just write it as 2 squared times 1. And then the last one is going to be plus 3 squared times 1. And if I add all these up, so this is going to be 0 plus 1 plus 4 is 5 plus 9 is 14. And so this is the left-hand approximation. Okay. Now that's good, and this we can find by finding the by drawing the picture and drawing the rectangles. But it's a good idea to know how to write this out as a sum, because this is going to help you out when you take calculus 2. So we're going to first remember that the left-hand approximation, this is the formula for the sum. So let me separate this right here. Okay, so we have, what we're going to have is the sum from 0 to n minus 1 of f of x sub I times delta x. And remember what these represent is that this means you're going to add up. Remember, f of x sub I represents the height, and delta x represents the width of each one of those rectangles, and so the sum is just going to add up each one of those. And so notice this sum that we have up here, this is what this pretty much represents. So like, for example, if you take a look at this first 0, that's f of x sub 0 times 1, which is delta x. Notice delta x is the same on each one. And then here we have f of x sub 1, and then f of x sub 2, and then f of x sub 3. Okay, so what we need to do is, well, we know that delta x is equal to 1. And it's always equal to 1 because we found it right there. And that's going to be fixed. Okay, but what we need to figure out is an expression for x sub I in terms of this I here. And I know this is kind of weird right now because you're not really that familiar with the notation, but let's try to work through this. Let me before we come up with the expression, let's write down a couple of things. First, we know that when I is equal to 0, x sub 0 is going to equal, this is the first x value, which is 0. Okay, then when I is equal to 1, x sub 1 is equal to the second x value, which is 1. When I is equal to 2, x sub 2 is equal to 2. And when I is equal to 3, x sub 3 is equal to 3. Okay, so it turns out actually then, if you look at this, you look for a pattern, you notice that x sub I is actually just I. And that's really it. It's as simple as that. And it can get a little bit trickier, and in the next calculus class you'll have to figure out some more complicated ones. But for us, we just want to get an idea of what this looks like, and so that next semester, when you take Calculus 2, you're not completely lost when you see these sums. Okay, so once we have that, well, why don't we rewrite, if we know what what x sub I is, why don't we write down what f of x sub I is? Okay, so all we're going to do is substitute. So instead of x sub I, we're going to put what x sub I equals, which is I. And f of I, well, the function is x squared, right? So f sub I is just going to be I squared. Okay, and then once I have that, this is really the keys that I want to figure out an expression for f of x sub I in terms of I. So this is basically what I was looking for. And so then the left hand approximation is going to be the sum from 0 to n minus 1, which is 3, of f of x sub I. Well, we just talked about that. That's going to be this guy right here, I squared, times delta x, which is simply 1. And notice that if you expand this sum, what you basically get is this guy that we have up here, because this is going to be 0 squared times 1 plus 1 squared times 1 plus 2 squared times 1 plus 3 squared times 1. And this is equal to 14, just like we found up here. Okay, now you might be wondering, well, if we did it up here, why do I even have to go through all this mumbo jumbo with all these symbols? Well, two things. One is that we want you to start getting comfortable with the summation, so that you can prepare for next semester. And also, we're going to need this to be able to find the exact value of the integral, this one that we have up here, using the definition, using limits. Okay, now let's do the middle approximation. Now this, we're going to go through it a little bit faster, just because we went through most of the nitty-gritty on this one, and this just basically changes where we're going to evaluate the function. So here we evaluated it at the left endpoint. For the middle one, we're going to evaluate in between the two. So delta x is going to still be the same, 1. A is not going to change. B is not going to change. What does change is where I evaluate. So I don't have room to draw the picture, but basically what I'm doing is I'm going to evaluate, bring up my rectangles are going to come up right here instead. So this is going to be, I'm going to evaluate at 1/2, 3/2, 5/2, and 7/2. Okay, so, well, that's not very difficult, right? Because so that means that the area, I forgot, over here, this should be approximately, sorry. The area underneath the curve between 0 and 4 of x squared dx is approximately equal to, so I evaluate at 1/2, so I'm going to have, the height is going to be 1/2 squared times the base, which is 1, plus 3/2 squared times 1, plus, I'm running out of room here, 5/2 squared times 1, plus, 7/2 squared times 1. Oh well, too bad. Okay, so this is equal to 1/4 plus 9/4 plus 25/4 plus 49/4. And if we add these up, we get, this is 35 plus 49, so this is 84/4, which is equal to 21. So if we use the midpoint approximation, we get 21. Now, let's try to do the same analysis here for the midpoint formula. So to do the midpoint formula, now the summation formula is very similar, except that we're using the endpoints. Now for the left one, we start off at 0. I equal to 0 because we're talking about I equals to 0 represents, or x sub 0 represents the very, very left endpoint of the function, of the integral, I mean. So for the midpoint, we're going to start our index at 1 and go up to 4. Now, here, I'm going to symbolize, I'm going to write down f of x sub I star. Instead of f of x sub I, I'm going to put f of x sub I star because what it is that since I'm using the midpoint, it's not 0 and it's not 1, it's actually right in between. So the star is the conventional notation for that. But don't worry too much about it. I mean, we're going to basically do the same thing. And so first, let's just say that delta x is equal to 1, and we're trying to figure out what x sub I star is, just like last time over here. Okay, so let's write some stuff out. So we know that when I is equal to 0, sorry, I is starting at 1. So when I is equal to 1, x sub 1 is equal to, so my very first value, which is 1/2. When I is equal to 2, x sub 2 is equal to 3/2. When I is equal to 3, x sub 3 is equal to 5 halves. When I is equal to 4, x sub 4 is equal to 7 halves. Okay, now this one is a little bit trickier to find out the formula in terms of I. But notice that each one is, well, it's 1/2 less than I. So when I is 1, x sub 1 is 1/2. When I is 2, x sub 2 is 3 halves. So what we can do is write it as I minus 1/2. Okay, so then if we know that, then that means that f of x sub I star, well, then f of x sub I star is going to equal I minus 1/2 squared. And this guy is what's going to go inside of the summation. So here what we're going to have then is, if I write this out as a sum, it's going to be the sum from 1 to 4 of this guy right here, I minus 1/2 squared, times delta x, which is, we just decided is 1. And notice, if you compare this one and this one, it's basically the same thing, because we're going to have, if you plug in 1 for I, we would have 1 minus 1/2, which is 1/2. 1/2 squared is 1/4. Plus, if you plug in 2, you would get 3 halves squared, which is 9/4, and so on and so forth. Okay. So, alright, why don't we work through the right endpoint one this time. So for the right endpoint, the same thing. Delta x is 1, a equals 0, b equals 4. And so we can say that the integral between 0 and 4 of x squared dx is approximately equal to, let me block this off right here, approximately equal to, so now this time for the right endpoints, we're going to use not the very first value, but the second one. So we're going to start off at 1, then we're going to go one more to 2, then the next one, which is 3, and then the last one's going to be 4. And if I draw these rectangles, notice that what's going to happen is these are going to be bigger rectangles in this case. And bigger even than the midpoint. And so this is the area that I'm finding right now when I expand this out. Okay, so what I'm going to have is, I'm going to evaluate, the first one's going to be at 1, so I'm going to have 1 squared times 1, so this is the height times the base, plus 2 squared times 1, plus 3 squared times 1, plus 4 squared times 1. Just 1 plus 4 plus 9 plus 16. And so this is going to be 5 plus 9 is 14. So this is going to give me 30. And so these numbers correspond. You know, I mean, we expected this one to be the biggest one, the right endpoint, because of the shape of the graph. Okay, now let's do the same thing here, the same thing that we did over here. We'll move a little bit faster through this one. Here we're going to use the from I equals 1 to 4, and now I just keep it as f of x sub I times delta x. And so here you can look at the difference. Here for the left one, we start at 0 and go up to 1 less than what n is. So here it would be from 0 to 3. The middle one, we go from 1 to 4, but we put a star there to symbolize that it's going to be in between each of the values. And then here we're going to go from 1 to 4. And so the same thing, delta x is going to equal 1 still. We already know that. And we want to figure out an expression for x sub I. Well, this is actually a lot easier than it looks. When I is equal to 1, x sub I is equal to, that's the first value that I evaluated at, which is 1. When I is equal to 2, x sub I is going to equal 2. When I is equal to 3, x sub I is equal to 3. And when I is equal to 4, x sub I is equal to 4. And that's it. And so, well, we notice that actually it turns out that x sub I for this one is exactly the same for the left one. It's just that I'm starting off at a different index. So then that means that f of x sub I is equal to I squared. And so then what I have is the sum from 1 to 4 of I squared times 1, which is going to equal 30. Which is exactly the same thing that I had up there. Okay, so that's good. Now that I have the formula, the sum, what I'm going to write is, so this was part, so this that we did was part B essentially. Okay, now what I want to do now is use these formulas that I found, and you actually remember we said you only need to use one. It matters absolutely nothing which one to use. But you want to grab this guy and you want to take the limit as n goes to infinity. So if I write down the general expression, I'm going to write down the left one. But you can write down the right one. The middle one is a little bit more difficult to calculate just because the index is different. So I'm just going to write down the general expression. We're not going to use 4 rectangles like we did here. We're going to use just n. And we're going to leave it as a variable. But we still have our endpoints the same. A equals 0, B equals 4, and so then delta x is going to equal B minus A over n, which is 4 over n. Okay, now for these it was easy to come up with, but let's write for the general form of x sub I is A, which is your left endpoint, plus I times delta x. So this makes sense in our example as well, because A is 0, and then when I is equal to, let's say 1, x sub I is equal to 1. And when I is equal to 2, x sub 2 is equal to 2, and so on and so forth. What this basically means is that you're going taking a delta x step from each previous one. So you go from 0 to 1, then from 1 to 2, 3, 4, because delta x is equal to 1. So then that means that f of x sub I is equal to, well, here, let's find what this, a is 0, and then I, we have to leave it as I and delta x. So x sub I is equal to, delta x is equal to 4 over n, so x sub I is equal to 4I over n. So f of x sub I is equal to 4I over n squared. Okay. So with that, that gives us enough information to write down the sum. So remember, the idea is that this, so we have the sum from 1 to n of f of x sub I, which is 4I over n squared, times delta x, which is equal to 4 over n. And remember that the idea is that if we take the limit as n goes to infinity of this guy, this is going to equal to the exact area underneath the curve from 0 to 4 of x squared dx. Okay, now to actually find this, well, let me write it down on a separate sheet of paper. So what we're trying to find is the limit as n goes to infinity of the sum from 1 to n of 4I over n squared times 4 over n. Okay, so the first thing we should do is take out the constants. And so what we're going to have is this is equal to the sum from 1 to n of, so here let's just square all this. This is going to be 16I squared over n squared times 4 over n. Now notice that, well, 16 times 4 we can multiply, that's 64, but all these guys aren't dependent on I, they're just dependent on n, and so these are constants, so if we take them out, this is going to equal to the limit as n goes to infinity of 16 times 4 is 64 over, take out the n squared and the n, this is going to be n cubed, and this is going to go from 1 to n of I squared. Okay, now this guy though, this we know what this sum is equal to. This sum is equal to, we have the formula for it. It's n times n plus 1 times 2n plus 1 all over 6. And so then why don't we put that in? So what we have is the limit as n goes to infinity of 64 over n cubed times n plus 1, 2n plus 1, all over 6. And this limit exists, right? Because, well, let's do a little simplifying. Here, why don't we just reduce these guys? This is going to be 32. This guy reduces to 3. We can cancel one of these ends and be left with 2 with this one. So here what we have is the limit as n goes to infinity of 32. Let's just FOIL this out. This is going to be 2n squared plus 3n plus 1 all over 3n squared And this limit is just going to be 64 thirds. And so this is the exact area underneath the curve. And notice that it's between the 14 and the 30, and it's actually pretty close to 21 in this case. Okay, so now let's do this. Let's find this using the absolute easiest way, which is the fundamental theorem of calculus. So using the fundamental theorem of calculus, this problem, it becomes very, very, very easy. And that's why the fundamental theorem is so important. So what the fundamental theorem of calculus says is to find the area underneath the curve, get the antiderivative of this guy. So the antiderivative of x squared is x cubed over 3, and we're going to evaluate it from 0 to 4. And remember what this is going to be always is top minus the bottom. So you plug in the top number. So this is going to be 4 cubed over 3 minus, plug in the bottom number, which is 0. So 0 cubed over 3. Well, this is just 0. 4 cubed is 64. And that's pretty much it.